Have you ever tried answering emails while someone talks to you, only to realize you've written something completely incoherent? That is cognitive workload in action, or the mental effort it takes to juggle tasks. Some situations push our brains to their limits, affecting performance, stress levels, and even safety. A recent systematic review set out to explore how we measure cognitive workload and where the field is heading. This study examined 2,411 research papers published between 2018 and 2024, focusing on five key areas: the science behind multitasking and mental overload, workload measurement tools like NASA TLX and MATB, and also Imprint from the US Army, emerging physiological methods like EEG and eye tracking, and the role of machine learning in predicting workload. The authors combined a systematic literature review, or the deep dive into published studies, with a bibliometric analysis, or big picture data mapping of research methods. Their goal was to identify the most effective ways to track, understand, and manage cognitive workload in today's increasingly complex world. So, what exactly is cognitive workload? Cognitive workload is really a fancy way of describing how much brain power a task demands. It's like a mental bandwidth. Some tasks require a trickle of effort, while others push your brain to full capacity. And as always, getting the balance right is crucial. If workload is too high, say an air traffic controller managing multiple flights at once, errors spike. If it's too low, boredom and disengagement creep in. The study highlights that by understanding cognitive workload, one can help improve performance, reduce stress, improve automation, and reduce human error. This makes workload research critical for everything, from designing cockpit controls to refining AI driven interfaces. Now, how is workload usually measured? The review identifies three main ways scientists measure mental workload. The first one is the subjective measures, or self reporting, and here they relied on NASA Task Load Index, or NASA TLX. It's a simple questionnaire where people rate their workload after a task. It's still widely used today because it captures personal experience, even if it's not always precise. This is very similar to traditional user research where we ask users about their experience with a product. There's also performance measures, task success and errors. This method looks at how well people perform under different workloads. For example, if someone starts making more mistakes as a task gets harder, that signals cognitive workload. Finally, and the most interesting, is their physiological measures. This is where things get high tech. The study explains that physiological measurements look at the physical reactions in the body based on the task, and using measurements like cardiovascular activity, eye tracking activity, respiratory changes, skin responses, and brain activity. These measurements are recorded during a task and then analyzed to determine the workload level. The advantage here is that it is objective and continuous. You don't have to rely on someone's opinion. Now, after understanding the basics, we have to ask, what is the cost of multitasking? We all do it, switching between emails, messages, meetings, and doing multiple things at once. Research says that multitasking is actually not efficient. The paper defines multitasking as performing two or more tasks requiring little to no overlapping of cognitive effort within a given time frame. And there are two types. There is concurrent multitasking, doing multiple things at once, like driving while talking on the phone, and sequential multitasking, rapidly switching between tasks, like jumping between tabs in a browser. The problem here is that our brains don't truly multitask. Instead, they switch focus. and this switching drains mental energy. The review found that multitasking leads to an overall decrease in performance, more brain connectivity, and the use of more cognitive resources. Although multitasking is shown to use more neural networks and parts of the brain due to a limit of mental resources, cognitive bottlenecking, which is an interesting term, can occur, decreasing the quality of the performance in all tasks being performed. Basically, when we try to do too much at once, everything suffers. Now, let's talk about these acronyms that I mentioned earlier, starting with MATB. The Multi Attribute Task Battery, created by NASA, is like a flight simulator for multitasking. During these tests, participants must manage system monitoring, like watching warning lights and dials, communications, listening to radio calls and responding, resource management, keeping fuel tanks balanced, and tracking, keeping a moving target in crosshairs. The study highlights that MATB is crucial because it replicates high stress environments like piloting. It is widely used to test how different workload levels affect performance and brain activity. And this takes us to Imprint. While MATB requires real participants, Imprint is a simulation tool. As I said earlier, it's developed by the US Army. It predicts workload in complex tasks without needing live human trials. Researchers use it to model how workload fluctuates in high stakes scenarios like drone piloting or military operations. The study explains that in Imprint, a task should be broken down into its most basic steps, and each element of the tasks should be separated and given a weight value in 4 main categories: visual, auditory, cognitive, and psychomotor. A discrete event simulation can then be performed on the model to determine areas where mental workload spikes or exceeds a performance, decrementing workload threshold. The twist is that Imprint usage is declining. The paper found only 2 publications using it, compared to 292 using physiological measures. But something is replacing Imprint, and it is machine learning and physiological sensors. The study found that physiological measures of cognitive workload, specifically electroencephalography, virtual reality, and machine learning, are rising within the human factors field. New research is focusing on EEG brainwave analysis to track mental workload in real time. In fact, one study cited in the review achieved 90.17% accuracy in predicting pilot workload using EEG data. Note how most of these examples are also in high-stakes situations. But this doesn't mean that it only applies to these high-stakes situations like controlling a drone or military operations. Actually, multitasking research directly impacts how we design technology. For example, there's a lot of talk today about AI-driven interfaces. You can imagine a user interface that adapts its elements according to the mental workload of the user or the complexity of the task itself. The study concludes that with today's strive for more artificially intelligent and automated systems, understanding how to integrate those systems with operators can help improve performance and reduce stress. It seems that the future of cognitive workload research is real-time, AI-driven, and physiological. Instead of asking people how stressed they are, we're measuring their body's signals. And as AI gets smarter, it could soon predict mental overload before we even feel it. Which is, of course, something that can go both ways, good and bad. And as always, the challenge is in balancing technology and human limits, ensuring we create tools that help, not hinder, our cognitive capacity.